we've got quite a bit to cover, so we'll try and move it out quickly. Continuing on from our revision, hopefully this will take about an hour, and then we'll have a break and you can come and collect your test papers if you haven't collected them already, and then we will continue. Okay, so we've dealt effectively with revision of the first question on the exam paper, which is all about dead loading, live loading, resultant forces, and we're moving on into equilibrium. So, hopefully you all understand equilibrium. Equilibrium means when something isn't moving, and we'll limit ourselves to 2D. All the forces in the x direction must add up to 0, all the forces in the y direction, and the moment equilibrium. It's not spinning in space, so it's in equilibrium. So we use equilibrium to help us find reactions, and we also used equilibrium to help us find internal member forces. And we did so by saying, well, if we want to know what the forces are in a member, we would just cut through the member and expose at that location a shear, a bending, a horizontal. Otherwise, what we did, in effect, we never drew it, but what we were doing is we were saying, okay, here is my free body diagram, and because the system isn't moving, it's in equilibrium, and over here I'm cutting through a roller that has one unknown reaction, and I'm cutting through a pin here that has two, and I'm going to balance those forces. I'm going to say it's not moving in space and calculate those unknown forces. So I'll set this question up, and I won't do it in its entirety because of our time constraint, but I will provide you with the answer. So a question like this, where you have a UDR load of 2 kilonewtons per metre acting over the central 4 metres. And what the hell, let's make this complicated. We have a moment up here, and we also have a horizontal and a vertical force here. And we want to calculate the reactions. So, effectively we say, okay, that's going to be our free body diagram. And to make it a free body diagram, I have to draw my unknown reactions on there. We have a roller, which has 1. We have a pin, which has 2. And we say, okay, this system is not moving in space, so therefore it is in equilibrium. So that means, and I've chosen the wrong pen colour, I think, all the forces in the x direction equal 0, so let's give that one a go first. So all the forces in the x direction, I have a 5 kilonewton up here on the upstand, and I have my unknown reaction Bx, so thus Bx is equal to minus 5. In doing this question, this will probably save me looking at the first question on the test paper. So we have one of our unknowns. We have 3 unknowns, 3 equations of equilibrium, so we can solve. If you then move on to your forces in the y direction, which is sort of usually the next way we go, you would say, okay, I have my 2 unknown reactions. I have my minus my point load 10, and then I have my UDR load of 2 kilonewtons per metre acting over 4 metres, and all of that equals 0. So that won't actually tell me what either A or B equal. So now I need to take moments. Now when you take moments, because we define a moment to be an actual moment applied or a force times a distance, it's important we define at what point we take moments, and usually I go for A, the left-hand support, whatever that may be. Now, what I want you to realise here, a moment, okay, can exist directly as a moment. It can exist as a force times the perpendicular distance. So, if you cannot trace your force back to the point, it causes a moment. What I mean by that is I have a 10 kilonewton here. I can't trace it directly back to A. So everyone, I think, in this room knows when we look at the moment caused by the 10 force, it's 10 times 6 metres. It causes clockwise, the way it's drawn. It's rotating clockwise about A, so it's negative. My UDL load, 2 times 4. When we, when we assume an equivalent UDL load on for a linear loading, we put it in the middle. So that distance would be times 2 plus 2, times 4 metres. That's also negative. But in this instance here, we also have a moment applied, and a moment is a moment. We have a moment of 8. It's going clockwise, so we would just subtract 8 as is, because it is already a moment. And then finally, we have our 5 kilonewton. Now, this 5 kilonewton causes a moment too, because when I follow the arrow line back, it does not pass through A. A is down here, and this is the line of my 5 kilonewton force. So the perpendicular distance there, perpendicular meaning at right angles to the force, is, and I haven't put it on there, which I would need to, 1 metre. So it would then be minus 5 times 1. And finally, we have our BY force, which is 9 metres away, and all of that equals 0. So from that, we have a base for BY. And then, using equation 1, we can then solve for AY. So, in saying a moment is a force times a distance, if your force is vertical, your distance will be horizontal. If your force is, guess what, horizontal, your distance will be vertical. So with respect to the test paper you sat the other week, in the first question, there were horizontal and vertical forces. Where people got them wrong was they forgot to take into the account the moment caused by the horizontal component. Okay? So horizontal forces can cause moments. An applied moment, it doesn't matter where that 8 kilonewton was applied. That 8 kilonewton, I could have actually applied it up here at the other upstand. I could have applied it here. It doesn't matter, it's already a moment. So you might say, well, why the hell doesn't it matter where the moment is? When I spin my pen here, I can hold it here at the tip and it spins round. I could then hold it at the other end and spin it and it spins round. And it spins round the same way. So it doesn't matter where the moment is actually applied, it causes the same reactive moments, the reactive forces. Okay, so that is equilibrium now under control, and now we're going to move on to trusses. So hopefully you remember a truss is a triangulated structure, and trusses, internal forces in truss members are only tensional compression, they're axial only, and that is because of the assumptions we make that all the joints are pinned. And when we apply all the loads, we're applying them at the joints. So in order to find the internal member forces, well, usually first things first, you calculate your reactions, and then you would find the member forces by the method of joints or sections. Nowadays, we specifically say using the method of joints, using the method of sections. So if you choose to do it the way not asked to do it, you won't get full marks even if you get the right answers. So you have to do it the way you're asked to do it. So certain things to remember here. With the method of joints or the method of sections, what do? We actually consider a free body diagram again. Let me just see if I've got this in here. Okay. We consider a free body diagram again. For the method of joints, it circles around a joint. For the method of sections, it cuts through it includes more than one joint in there. Oh, here we have here. Okay, method of joints, method of sections. Sorry, let me just remind myself. Okay, so looking at the method of joints first. With the method of joints, because we're only considering a single joint, you can see here that you have no moment happening. We don't give you trusses with moments applied to them. So all these forces, if you do trace them back, they all trace back to the joint. Thus, the moment equation is not helpful to us here. So we only have two equations of equilibrium to use. So with the method of joints, you can only have two unknowns at a time. So over here, you couldn't solve this system because you have three unknowns. So with the method of sections, you cut through the section, and when you do, because it's a truss, typically you cut through three members, and we have three equations of equilibrium. We can use our moment equation this time because all our forces aren't concurrent. You can't trace all these forces, and the forces I'm talking about are our reaction force here and these unknown forces back to one point. So we can utilise our third equilibrium equation, the moment equation. Now the thing with the method of sections, I just so dislike when I hear I get the method of joints, I just don't get the method of sections. The method of sections is not the method of sections, it's equilibrium. That's all it is. So there's nothing not to get. But the trick with the method of sections is when you take moments, always take moments at a point where two of your unknowns meet or are concurrent. So in this instance here, you can take moments at x, because taking moments at x, can you see when you've traced back your unknown forces, F23 and FC3, they run through the point x. So they won't be in your equation. Or you can take moments at y. So, as I've said from day one, you can take moments on the moon if you want. So don't think where you're taking moments has to actually be within your structure. In this point here, point y actually corresponds to this point up here. So the point where you take moments about can be outside of your structure. Okay, here's an example here. 2007 paper semester 1. There was too much information given in this exam paper, so we had to put an irradium, whatever you call it, in the paper and say ignore these angles because they weren't correct. Okay, we have a print jointed truss. I would call this the scare question. This looks different to your normal trusses. You'd look at that and go, oh my God, oh my God, oh my, you would say. And if you do have that response to this type of question, what you should do is you should then turn the page and move on to another question. So don't tackle any question in a panic. Okay, we have a truss and we are asked to calculate the forces in members C, E and CD that are coloured in green here using the method of joints, working through a number of joints. So it's telling you you can't start off here because if you try and start off at that joint, you have three unknowns. So you have to work your way through. Now, working your way through, you're better off working your way through from A and B rather than H, because if you work through from H, you'd have to look at joint H and then you'd have to go to G and then F and then E. Whereas if you work the other way, you would only have to work through joint B, A and C. So, in order to start at joints A and B, you need your reactions, and people went wrong, once again, calculating their reactions because they, once again, made the error of not considering the moment effect of a horizontal force. So, you would start this problem here by drawing your unknown reactions, positive, based on the sign convention. And you can very quickly solve for those forces. So looking at forces in the x direction, we know we have AX plus 50. So AX is equal to minus 50 kilonewtons. I'll now take moments. And I'll take moments at A. So taking moments at A, we know we have 50 times our height here, and this is the issue. We don't know. We have been given a dimension 3 metres, but we don't know this height here. But what we do know is we've been given an angle of 30 degrees, so we know that angle in there is 30 degrees, and we have been told that that length there is 10 metres. So thus, this height here is equal to 10 divided by, hang on, I won't take a shortcut here because then I'll muddle myself up. Okay, we know the length ED divided by 10 is equal to tan 30 degrees. So a bit of trig in there. So that height in here is therefore equal to 10 tan 30 degrees, which when you work it out is 5.77 metres. So now when we take moments here, we have 50 horizontal force times the vertical distance from A. So that would be multiplied by our height of 3 plus 5.77. I put a negative sign in it because it's going clockwise. And then you would also have your 100 kilonewton and the perpendicular distance from A. The full distance is 4 plus 6 times 14. And then we would have plus 4by. So from this, we get a force for B, a value for by. And then using equilibrium in the y direction, you get a force for AY. Now it is very disheartening, so for my sake, don't make an error in your reactions. Do that just for me. You could do it for yourself as well. But there's nothing worse than when the error is in the reaction, so you know that means every other number is going to be wrong. Okay, so we have our two reaction forces here. Which joint shall we start at? B. Now you might think, my goodness, they're making me go through, oh there you go, first, second, third joint, 3 joints to get there, but joint B is a dead easy joint. So working through joint B, we know our reaction force here, 495.6. So doing a proper, I'll just do it on this joint. Forces in the x direction equals 0. I do want you to draw your joints out every time. The more you put down on the page, the more neater you are, the less likely you are of making a mistake. So at this joint here, very quickly, you can see that FAB equals 0. And in actual fact, we don't even need to know what FBD is. So after this joint, we can then move on to our second joint. Now, I'm not going to do this, the rest of the joints. I'm just going to draw this out for you and point out common mistakes made. So if you can't do a method of joint, that's okay. You've got 3 weeks before you have to be able to do one. So just make, or 2 weeks, just make sure you can do one before then. Okay? So the force is here. This is a common mistake. The reaction force we got here was negative. That means it's pointing down. So people, 5% of students would then draw that in the wrong direction. Now another 10% of students, where they would go wrong is they would forget to put the horizontal reaction in there. So don't forget that horizontal reaction here that we calculated of 50 kilonewtons. So when you draw your joint, go, oh, is this a pin joint? It has to have 2 reaction forces. Not even 10%, maybe 15% of people would have forgotten to put that 50 there. So anyway, once again, the forces we're interested in are that force and this force. So you can see we don't even need this. So you don't even have to bother, well, you do in this case, because you need that to calculate the other one, but check what you require and work through it. So that would be joint C, joint A, and then you would then move across to joint C. So I'm not going to do that now, because that's just a simple method of joints. What I want to focus on is the method of sections. Okay, let's just go back. For the method of sections, we're asked to calculate the forces in DF, DG, and EF. So take your highlighter with you or your different colour markers and pens and mark on there. Okay, I want these 3 forces, so it's pretty obvious where I would consider my free body diagram. Now when I say it's pretty obvious, I have drawn a blue one And you could, if you wish, say, no, I'm going to consider my yellow free body diagram. So you have two possible free body diagrams, free body diagram 1 or 2. If you made a mistake with your reactions and you use free body diagram 2, that mistake would be carried on through. So for this problem, I would consider free body diagram 1 when I calculated those forces. So just setting up that method of sections for you. What you need to do to reduce the chance of making errors is to actually draw. You're going to be given a booklet with lots of pages in there. Make the most of it. So redraw and tell yourself, I'm drawing all my known forces and I am drawing all my unknown forces. Now, on this system as well, I'm going to include, didn't want yellow, this joint here, D, to show that I recognise these two unknowns, FDF and FDG, run through them. So I can use that potentially as a point about which I'll take moments. Now, as we calculated this length here to be 10 tan, what was it, 30? This length in here, if we need to know it, is 6 tan 30, because that distance in there is 6 metres. So we can, now when you take the forces in the y, so you have 3 equations once again you can use. Forces in the x direction, that won't give me anything directly. It'll give me an equation with 3 unknowns in it. Forces in the y direction, that won't give me anything directly either. And then we can take moments. Now, what you can do is you can actually take moments at a number of points to calculate your unknowns. So you don't even have to use this equation, forces in the x direction. You could take moments, in this case, at D or at F. So if I take moments now at F. So taking moments at F, and this is where people get confused, I have this force here, FDG, going off at an angle. So we know our force is a force times a perpendicular distance, so I could work out that perpendicular distance in here, but I am likely to make an error because it's exam conditions and I know I'm likely to make an error. So what you can do is you can say, okay, I'm going to resolve this force FD up into a sine component and its cos component. And where did I get that 30 from? That angle in there is 30 degrees, so that angle in there is 30 degrees. So now, when I take moments at F, which is that point here, you can see FDF runs straight through the point, so no lever arm, no distance. FEF and FDF don't cause a moment. So the forces that cause a moment, this 50 kilonewton causes no moment because you can trace that arrow through the point. So the only forces that cause a moment are the 100 times 6 metres. About F, it's going clockwise, so it's negative. Now, this FDG sine 30, does that cause any moment? No. Times 0 metres, because you can trace that load through. So the only other force we have is our FDG cos 30, and we need that distance in there, which we said was 6 tan 30. So from that, we can solve for FDG, which gives you a value of minus 200. Now, you could then choose just to then go back to your forces in the x or forces in the y direction, or you can then just take moments this time at D, and taking moments at D here, can you see what force you would solve for? You would solve directly for FEF. So I will leave you to do that yourself, to finish off that problem. And all answers to past exam papers you will find online on the exam paper itself, themselves. Okay, so that is stresses under control. Then we moved on. That was analysis, calculating member forces. Then we had a look at deflections and design. Axially loaded members. These three formulas should be familiar to you. The first formula here will tell you how much a member that's axially loaded will expand or contract. What can I say about this? All I can say is be consistent with your units. And also, get your units correct. Okay? Make sure you know what units you're working in. Okay? When we have a member in tension or compression, we know to design them. For member in tension, we just need to check yield. And for a member in compression, we need to check yield and buckling. So, here we go. Under compression, a member, and I didn't bring my ruler, but I've brought it enough times for you to know, will either buckle or yield. If it's long, it will buckle. If it's short, it will yield. What do I mean by yield? It will squash. I think of a piece of fudge. When you squash a piece of fudge, it'll ooze out. It's a ductile, we're saying. So, therefore, for a member in compression, you need to do both checks. And on the exam, you'll find we're always asking you to design members in compression because we want you to use the buckling formula. Okay, semester 205, I don't think this one's online yet. This is a good question. Have a read. Do I need to read it to you? Okay, we have a bar AB. It's supported by a pin joint down here at A. Oops. And a roller against a smooth wall. What does that word smooth in there imply? It implies there's no friction, so there's only one reaction here. Now I am drawing it to the right because I have the habit of always drawing my unknowns positive to my sign convention. I am expecting that to work out to be negative. If you want to draw it the other way, feel free to do so. So, before we read further, we go, okay, here are our three unknowns. Our bar is a solid square section, and it's 65 by 65 square section, and we're given a yield stress of 50. 60 kilonewton force is applied vertically down at B. Part A, calculate the force in bar AB. So people get confused by this. Method of joints. That's all you need to do here. So when I say method of joints, you'd say, okay, I'm going to consider that as my free body diagram. And in that free body diagram, I draw the forces I know, the forces I don't know. So in this instance here, we're using the method of joints not to solve for an internal force, but to solve for a reactive force. Method of joints just applies to forces. Method of joints doesn't say it has to be an internal force, it has to be a truss. Okay? That's why I'm saying we give it this wonderful name, the method of joints. I could just be saying it's equilibrium again, guys, which is what I've been saying. Okay? It's just equilibrium again, but it sounds so much harder when we call it the method of joints. But it's nothing harder than that. Okay, you have been given enough information there to calculate your theta value here. So you can do a method of joints. And I won't do it for you. I will let you do it. So you would look at forces in the y direction equal to 0, and from that you would solve for FAB, and the force in FAB will work out to be minus. And what does that minus sign mean? It means it's in compression. So going back to this problem, our truss problem, if you look at past exam papers, you'll see there's always a box at the bottom that would say member here, and it would have, it doesn't even tell you the member, and whether it's compression or tension. Oh no, it does. It'll have FEF, FDF, and then you would be asked to calculate, put the load in, and whether it's tension or compression. So when you put the load in here, if you put in minus 100 and say it's compression, you would get the mark. If you put in 100 and say it's compression, you would get the mark. So we're not too worried about you there doubling up on the negative. What we look for here is the word compression. If you put in negative 100 and call it tension, you won't get the mark. Okay? So whenever you get a negative value out, because that is an internal force, that means it's compression. When I would then work out the value of Bx, a negative doesn't mean compression. A negative, because it's a reaction, means pointing the other way, going in the opposite direction, which in effect is the same thing, but we'll just leave it there. Okay, so we now have the forces here. So we've done part A, we've got 20%. Due to shortening of the bar, its end drops from B to C vertically. Calculate the vertical, calculate the vertical distance BC. So it's asking us to calculate this dimension here. Now to calculate that dimension there, what you just need to do is you need to look at your original system, where that's 3 metres and that's 4 metres, and using Pythagoras you know that that is 5 metres. And then you need to look at your final system. Now when I say your final system, this dimension 4 doesn't change, and this is the dimension we're after. This is the one we're interested in, so I'll call that A. Now this length here, our member was originally 5 metres long. It's carrying a compression force of 100 in it, so it is shortening amount PL on AE. Based on that P being 100, I'll write it as kilonewtons. So this is where you have to get the units right in here. So therefore, this new length in here is 5 minus delta. Now I'm writing 5 minus delta. You need to get your units correct. If you choose to work in millimetres here, realise it would be 5,000 minus delta. Okay, but anyway, based on Pythagoras, A here is equal to, 5 minus delta all squared minus 4 squared. And that dimension there, when we work it out, actually works out to be 4.99831 metres. So thus, oh no, sorry, what am I saying? This dimension in here is 4.99831 metres. And when you use Pythagoras, and work that all out in there, you will actually get that dimension there to be equal to 2.997 metres. So therefore the drop here is 3 minus 2.997, which works out to be 2.82 millimetres. Okay? Nothing hard there. That again would be what I would call the scare question. It is a bit scary when you first look at it, But just remember you can do everything on that paper. Okay, part C. Again, I'm not going to do it all. You know it's a member in compression. You're asked for the buckling capacity of the bar to check whether it's adequate for design. Also calculate the squash load. If you are not familiar with that terminology, the squash load is the yield stress times the area. So that's the maximum load it can carry before it squashes. So with this problem here, our section has a buckling capacity of pi squared EI L squared, which is pi squared. We're given the Young's modulus of 70,000. Our section is a solid square section, so BD cubed on 12. And in this case here, when you come to put the length in, you can just stay with your 5 metre length. And that gives you a value of 41.1. I just want to get my units correct. That would be by 10 to the 3 newtons, which is 41.1 kilonewtons, which is less than the acting 100 kilonewtons, so therefore it would fail in buckling. Now, if you forgot to do that buckling check and just considered the thing yielding, squashing, the squash load here is your yield stress of 50 MPa times 65 times 65, the area, which is 211.3 kilonewtons. So if we actually look at our P on L curve, we know it looks like so. We're saying this upper limit here is our 211 kilonewtons, and we're currently at 5 metres long, sitting on that point in there on our graph. Okay. Any questions? See me in the break. Let's move on. Beams. See me in the break, ask me, and then I can always go back to it if it's a valid question, rather than now. Sorry, we're pushed for time, and I think I have more than usual, so I think that's because people want to come and get their test paper. Don't worry, I took advantage of that by stating that would be what I was doing. It's nice to see so many faces at the last lecture. Or did you come just because it was the last lecture? No. Okay, I know you're not sentimental. Okay, beams. Beams carry load by bending and shear. We've just covered trusses. In trusses, we had axial and tension and compression loading. For beams, beams curve. So now when we cut through our free body diagram, we have a possible axial force as well, but bending and shear. So we can only make one cut with our 3 equations of equilibrium. So for a beam, the internal forces are axial bending shear. One cut gives us 3 unknowns. Easy peasy how to plot a shear force diagram. Start at the left-hand end and follow the loads. You can't get easier than that. In saying that, calculate the right reactions, please. Okay? If you have time in the exam, and I know it is stressful, calculate reactions twice. Okay? So in this problem here, it's symmetrical, but I would take moments at A, solve for them, and then very quickly take a moment at B and check I get the same reaction. So you're 100% you got it right. That's if you're unsure, if you know you're prone to making errors. If you don't make errors, don't worry about it. Okay, you start at the left-hand end. You follow the vertical loads in this case for a horizontal beam. Shh. We step up. When we have no load change, we just move horizontally across. We step down wherever we have a load, we move horizontally across. Bending moment diagrams. Very importantly, we utilise the relationship between shear and bending. Shear is equal to, when you draw your shear force diagram here, we know it's the shear force diagram, but it also represents the slope. When I say slope, the gradient of the bending moment diagram, and that's because V is equal to dm dx. So the fact that you have a positive value here means your gradient of your bending moment is positive. Now, in saying that, a positive gradient is a downward slope, and that is because we draw our bending moments positive down. So it's a minor thing, but an important thing for you to remember. So, for plotting the bending moment diagram, you know you draw your bending moment on the side of the beam that's stretching in tension. So if you can imagine how it's deflecting, that will help you to start off with. You mark where the moments are known to be 0, and you start plotting. So rather than run through that, I'll go do an example. Bending moment diagram. What is a positive bending moment? We know a positive moment itself is anti-clockwise, but a positive bending moment is, as I always said, a happy bending moment. It's positive. So anything that sags like that, you should be getting a positive value for your moment. Anything that is sad, okay, is a negative bending moment. So as I said, what that means is we plot bending moment down. The business about drawing the bending moment of the side of the beam in tension, here I have a simply supported beam with a bit of a cantilever on the edge, and I have 2 point loads applied. Now, hopefully you can imagine what the deflected shape here looks like, drawn in red dashed. If you can't, go and buy yourself a nice flexible ruler or a bit of flexible moulding like I used to have. Take it in the exam with you. As long as it's not big and vicious and they consider it to be a weapon, I'm sure they're going to let you take something short in there with you. Okay? Put your pens on your desk, take extra pens in there, take fat ones so you can put it on your desk and you can apply your fingers, UDL load, point loads, and see how it deflects. And then make use of that. Because I have tension on the underside of this beam, so I'm going to put a tension here, I know my bending moment will be below the axis. Because I know I have tension in the top of the beam, I know my bending moment will be above the axis. So that will help you draw your bending moment diagrams if you're having problems. Now, where your bending moment is 0, and this is the question I'll do on the test paper, where your bending moment is 0, that corresponds to a point of inflection. Because what is a point of inflection? It is the point in the beam where you have no stresses, where you get this double curvature thing happening. There's your point of inflection. No stresses, no curvature, no moment. And I'll talk more when I do the test paper. Okay, here is, again, another scare question. I can do bending moment diagrams. Oh my goodness, what is that doodle-lucky thing hanging off the bottom there? I've studied so hard and now they've given me this crap question that I can't do. You can do every question on the exam paper. If you panic, turn the page and go to the next question. Okay, have a look at that one. I'm not going to read it. I need a rest from talking. Okay, we ready to tackle it? I will push on because it's going to take you a while to collect your papers. Okay, shh. Think you can do it? Okay, there is a little bit of a trick here. You probably, well, without that, you could still calculate your reactions. Reactions, force times distance when you're taking moments. So if you were taking moments at A here, you would, when you would put an equivalent point load on here, you would say I have 40 kilonewtons acting here, and you could calculate your reactions. However, when it comes to the bending moment diagram, take note, you're asked to plot the bending moment and shear force diagrams for the straight part only, for A, B only. So we need to get rid of this dag hanging off the bottom here. So we want to remove it. So how you would remove it is you would say, okay, hang on a minute. if I draw this free body diagram here, I know I have 40 here. When I cut through here, I know I have a shear and a bending and an axial. I know I have, for equilibrium in the y direction, I must have a 40 upwards. And those two forces as applied, can you see they create a couple? They create clockwise rotation. So up here, you would also have a moment. And that moment, that's 6 metres. This moment here would be 40 times 6, which is 240 kilonewton metres. So far, so good? Now, they are the reactions on this part of the beam. So if I want to remove this completely from the system, I then have to apply the equal and opposite forces to my actual beam. So if I want to consider that dag hanging off there removed, I would say, okay, well therefore I'm going to put a 40 kilonewtons here, and as well as that, there's a moment applied here of 240 kilonewton metres. So they are in effect the resultant forces that that beam AB experiences. So now when you do the problem, here we have, just a moment, oh yellow, I don't want yellow. We say we have a moment of 240 and a force here of 40, and we ignore all of that. Now I will leave you two to calculate those reactions, but make sure you get 51 and 53. So once you do those reactions, it's quite a simple exercise to now calculate the shear force diagram. You step up a value of 53. The load reduces by 8 kilonewton per metre as you move out, so it's a linear reduction. So by the time you move out 8 metres, it has dropped by 64 kilonewtons. So that would take us down to 11. Now, one other point, please be neat. If I can draw a relatively straight line in front of all of you, you can do one in the exam. People do lose marks because they're messy, not because I sit there and go, that's messy, I'm going to take marks off. It's because I'm sitting there going, I have no idea what they're doing. Okay? So you need to have legible calculations. You don't, as an engineer, when your calculations go through to the checking authority, if they don't understand what you've done, they're going to send them right back to you and say, not clear enough. Okay, now we have a force of 11 here and we have a moment, no, the moment doesn't come into it. I do have a point load that brings us down 40. There's no load applied, so it brings us down a total of 40 to a value of 51 kilonewtons, and thank goodness that's the value of my reaction here. So all the forces in the y direction add up to 0, so I am happy. So I know I have got the right shear force diagram. If you get to the end and you go, I step down, I've got a value of 49, and I step up, oh my goodness, I'm not stepping up to 0, I'm at a value of 2. That is your numbers telling you to go back and check and find where your mistake is. Okay, so believe your calculations. Okay, shear force diagram, easy enough. Bending moment diagram. What's the bending moment at a pin end support? 0. What's the bending moment at a roller end support? 0. So we've marked where there's 0. In terms of deflected shape, we know it's going down. There's a moment on there. Oh God, what's that doing? Not sure yet. So don't bother taking the deflected shape any further. Now you're going to utilise the fact that dm dx is equal to v. So what does that mean? All you need to do, as I said, I could just grab the next person that walked past this room that was good, that did a bit of maths and was good at following orders or instructions. A positive shear force means my bending moment's going to slope down. Through here as well, it's going to slope down. Oh no, then I have a negative shear force. What am I saying? A negative shear force means it's going to slope up. And through here I have a negative shear force, so it's sloping up again. So I have the directions of my slope. Easy peasy. My shear force diagram is linear, therefore my bending moment diagram is a parabola. Why is it a parabola? Because if v is equal to dm dx, m is equal to the integral of v. If I integrate a straight line, I get a parabolic line. Okay? Okay, so my bending moment diagram. I now know where it has 0 values. I know the way it's sloping. I know through here it's a parabola, and I know through here it's a straight line. So, I would hazard a guess. I would draw my nice parabola. If the slope has to change, that means I have a maximum moment here. So whenever your shear force passes through 0, that is where your moment is maximum. Okay? If v is equal to 0, dm dx is equal to 0, therefore your moment is a maximum minimum. So we come up here. How do I know how far to bring it up? Well, we do know that that area there will give me the value of that moment there. And thus, if I add that area on, it doesn't bring it higher. The issue you now face is, does it step up or down? Down. Just memorise it. Clockwise moment, it steps down. We can't put the value in yet, as yet, and we know our bending moment is linear and comes up. So you would need to calculate that value and that value there. Bye-bye to whoever walked out. Okay. That M2 value is very easy to calculate. I'll call that M2 because it's just equal to the negative area there. So that value there is 51 times, what's that, 8 metres, which is 204 kilonewton metres. To calculate the maximum moment, you can either work with areas. If you work with areas, you need that distance. To calculate that distance, what is the slope of my bending moment, of my shear force diagram equal to? Of shear force is equal to my load, 8 kilonewton per metre. So thus, if that is 653 kilonewtons, and that is x metres, and that is 8 kilonewton per metres, you can work out that x is equal to 6.625 metres, and then use the area method. I'll let you finish that one yourselves, and we'll move on. Okay, I don't think I have many more examples to do. I've got one more example to do before we have our break, and we move across to the project. Bending stress. What can I say about bending stress? Make sure, how many of you want to do civil? Good. Okay, my second years have just sat a test. Shh. And half of one question was just calculating centroid and moment of inertia, and about 30% of them got it wrong. You need to know how to calculate your moment of inertia and your centroid, so make sure you know how to do it. So you've been given the formula. I'm not going to run through it again. Just make sure you know how to calculate your centroids, your stiffnesses. This shift term confuses a lot of people. It is the distance. Just look it up in the notes from the section centroid to the centroid of your rectangle. That term is always squared here, so we don't worry about negatives and positives. Okay, deflections, we've just done it. I'm not going to do a deflection example. I did enough in the lecture. Indeterminate structures, we've just covered them. As I said, the last question has an axial and a bending one. I will do this problem here, which is the axial one. Have a read. We have a column. It's fixed at A. It has 2 point loads acting on it and a gap. So this would have been considered as the question on, one of the questions on there, where I know 50% of people won't be able to do it. I don't know why they wouldn't be able to do it. Well, I do, because they didn't turn up to one lecture or their practice classes. And they don't really want to be doing engineering, and they're only doing it because they got the marks to get in. Is that me being harsh? Oh, okay. I take all that back. It's because people haven't applied themselves to the best of their capability. Okay? Okay. Calculate the vertical reactions at A and D. Shh. Now, of course, for there to be a reaction at D, the member has to stretch it at least 10 mil, so we can check that. So I would definitely do this problem using superposition, where you have a primary and redundant, but I would actually break this one up into two primaries. So I would call this primary 1, where I apply one of my forces of 80. You could do them together if you want, but I think it makes things a lot clearer if you apply your two forces separately. And then we're going to assume we have contact. Well, we're not. We can work out how much it extends from the primary 1, primary 2 system. If that's greater than 10 millimetres, we know we have contact. But I'll just draw my 3 determinate systems here. And they all equal the initial system based on the compatibility relationship that, I'll call that delta primary 1 plus delta primary 2 plus delta redundant. So what does delta primary 1 plus delta primary 2 plus redundant equal? 10. Now, because we're dealing with 10 mil, you have to ensure when you use these problems you're dealing in units of millimetres. So, delta primary 1, it's PL on AE. P is 80 kilonewtons. What is L equal to? 2 metres. Delta primary 2. P is equal to 80. What is L equal to now? 5. Good. Make sure you get your distances right. When I come and work out now delta primary 3, it's equal to D times what distance? 8. What the hell is she talking about? This 80 kilonewton is only stretching this length here, 2 metres of length. So therefore that's why that's 2 metres. In my second primary system, this load is being transferred up to the top. It's only acting in 5 metres of length. When I consider the value D, that is acting throughout the entire 8 metres of length. So when you do plug in these two deflections here, primary 1 plus primary 2, actually add up to 17.5 millimetres. So that's telling us we do have contact. I'll leave you to finish that one off. You'll get a D force equal to 30 kilonewtons. And thus straight away you know your A force, because from equilibrium here, you would say A plus D minus 160 equals 0. So therefore you know A equals 130 kilonewton. Fair enough? So simplify things down if you can. Don't panic. Okay, extra hints. with respect to that first question, sometimes it says what's the loading on the beam. The loading on the beam always includes the weight of the beam itself. So when calculating dead loads in that first question, so this relates to question 1, always include the self-weight of the member itself. Don't leave it off. Okay, this relates to, I think, question 2. When required to size a member, this is if you're doing a buckling problem. So quite often you'll see section tables. We actually say choose a size that's sufficient to carry the load. Usually we define it as a minimum weight. We usually say choose the most efficient. So we might say the most efficient. So when we talk about efficient, we are referring to minimum weight. So when you use the tables, and hopefully you're familiar enough, you say I need an I value of this, you go up the I value column, you find the first one and you go, that member's good. Now you may find a member with an I greater than that, but is lighter. Okay? And that is because as you move up, your sections get bigger and their thickness reduces. And we all know when a section gets bigger, because the area is spread further from the neutral axis, so this could be a thicker section, and this one a thinner one, your stiffness increases but your weight might reduce. Okay, always draw your free body diagrams. I've said that already when doing the method of joints and sections and when deriving reactions and deflections to get consequential marks. Okay, the exam is worth 3 hours. It's 3 hours long. And it's worth 50%. For those of you that have got your test papers back, it is harsh to say, but usually there is a pretty direct correlation between who failed the test and who fails the exam and the subject. Not to say, and I'm not saying, if I draw my Venn diagrams, I'm not saying if you fail the test you're going to fail the exam. You have 4 weeks to get your act together and learn the material. Okay, 2. Okay, 2. Okay, what I am saying is, if you did poorly on the test, take that as your wake-up call. That mark staring you in the face is saying you need to work a little harder in order to pass this subject. In general, I know there are situations where maybe you had a headache, something happened, you weren't there, you know, in the room, whatever. Okay, you have to obtain, I think you're aware of this. We say you have to actually get 45% on the exam to pass. But you need an overall mark of 50. So if you get 45 on the exam, that means you need to get 55 for your continuous assessment in order to get an average of 50. The minute, if you get 80% for your continuous assessment, the minute you get less than 45 on the exam, you get 42 on the fail, it's an immediate fail. Okay? So you have to get at least 45% on the exam to pass the subject. Exam format is similar to previous years. God, if I change that, it would be disaster. Okay? The best guide, I say problem set test. I would actually say at this point in time, if you're on the ball and you know what's going on, do as many past exam papers as you can. 2 of them on there have full solutions, the others have answers. That's more than enough to give you. It's closed book. Please make sure you have that calculator sticker on your calculator. And as I said to my class, shh. Normally you're told don't bring pencils in. Bring a pencil in for your bending moment diagrams. If you do choose to work in pencil, don't erase anything. Don't. You write it, you go, that's all wrong, you rub it out. I can't see it. Well, I can if I hold it up to the light and I go, damn, they've ruined it for themselves. You put a line through, you start again, all your new working is completely wrong. I look back at your old working, it's all 100% right. I'm not going to give you 100%, but I will give you marks for that working. So don't erase anything, however tempting. You can if your bending moment line is really crap. Okay? Okay. Good luck. I propose to have 4 exam sessions, help desk, optional, where you've been through the exam papers and you can't do question 1 on this one, question 2 on this one and question 3 on that one, and you want to come in and get some help. Come and get some help. I will send an email out telling you when those sessions will be. Project 3, I just sent an email earlier about Project 3. Put your group numbers, please. If you haven't, don't worry if you've handed it to me. Group numbers on the report. Okay, I have test papers up here in order of your tutor, so you don't go through the whole part. So, I have Sina here, Tarek here, Tanvirul here, Jahadul here, Lucien here, Masa here, and Lawrence here. Come and collect, we'll have a break. Yes.
Project 3, I changed my group, I emailed you with the names.
So if you've emailed, I've got it. What I'll do is when I make the change, I'll email you back going, thanks for telling me.
Yeah, and I couldn't go for my tutor in the morning. That's Mike's class.
Have a look. If you did it in another class, you might find it. If you don't collect your paper today, they'll all be left in the office to collect. So have a look. If you did it in another class, it might still be there. Yes.
I was with Lee Chick yesterday, but I wasn't able to get to the shoot. So my exam going to be around somewhere.
So when did you sit your test?
I'm in Tuesday.
Tuesday. If you're doing Tuesday, it'll be in the office. I didn't bring anyone upstairs. Yeah. Can you give me a minute to get organised?
Oh, yeah.
Okay. Yes.
Lizzie, are they allowed to write with pencil in exams?
I don't have a problem with it. I'm not going to mark you off if you do it. So, yeah, for mine, I don't know about what other subjects say. As long as it's a nice, distinct pencil and I can read everything
Could you
clearly.
please upload the solutions of the deflections and everything?
Solutions to what?
The Moodle thing of the whatever the lecture slide in Kings.
Yeah, I put everything's on there now. Yeah.
The last year still before used to goes in there.
Yeah, no, I think I put everything on there except the revision.
Okay.
Yeah? Okay.
Excuse me. Can you explain one of those questions you did really early?
Yeah? Which one?
It was the one with the
Is it
trusses.
today?
Yeah.
Oh, the trust one?
So how did you know
Yeah.
that that was 30 degrees, given that
Oh,
these two
that-
have been crossed out?
There was a 30 degree.
Yeah, but what makes you so sure that this is parallel to the ground? It's top part. So?
It's drawn horizontal.
So you just got to assume what? So
Yeah, if it looks
there's
horizontal,
nothing.
it is.
It just looks horizontal. There's nothing
No,
actually
if
there
it
to.
looks it.
It is.
We're not going to put it 1 degree out or 5 degrees out. If it's not, we're going to make it an angle where it's obviously
Excuse me, just one simple question. I have already handed in the project to the tutor,
Was that
but I didn't write the group number.
okay? That's okay. We can be
Oh,
fine.
yeah.
Okay.
That's cool. You got more than I did.
Okay. They won't be there. They'll be in the office. I didn't bring the classes that have already been. Yeah, I didn't bring them. I only brought the classes that haven't been yet. Because I thought everyone went to their tube class. I assumed everyone went to their tube class and they're in the office. So after this, you can go to the office. The civil engineering office. Where you have to name your projects into. Building 60. Yeah, first floor, building 60. Yeah? You need to find it because you need to drop your reports projects in 2 days. Yeah? Quick questions while she's here? Yeah? Oh, okay. Hang on, okay. Yes? Hang on, this is a tape. I just touch the screen. No, that's all right. I just don't want to...
Okay. For the depends on the diagram, which this one is the maximum length of this one.
Well, this is the maximum, but this is a local maximum. So you'll see in the question, we always actually refer to them as, we actually say, where is it? somewhere. Okay, plot the bending moment diagram, indicate clearly the maximum and minimum values. I call them local maximums. In the test paper, so in the test paper, you'll see when it came to drawing these bending moment diagrams, it said show values of all local maxima and minima.
Oh, the local.
That's a local one. Yeah. Basically, if you had to draw that, if you said Lizzie draw it, you'd say put a parabola in and make the maximum value here and make it come up to a value here. So you basically need to put every value in wherever it changes slope, it changes direction.
What if this one is the local? We should write, for example, this one
That's
is
just
the
all
maximum.
values. So basically, wherever you have a change, you should put a value in. Yeah.
And I get confused with draw the deflected shape.
Yeah, can I, how about I'll talk to you after the lecture. Yeah. I'll answer some short questions. Yeah? Ricky?
It's about the bending moment.
Yeah.
Always my question is label the local maximum.
Yeah.
What is
What's the
is
like
there
that?
maximum and minimum?
No, so that's a local maximum. Because the maximum value's here.
Well, there is a minimum.
Basically, wherever there's a change, if you have to draw it, if you told me to draw it, you'd say draw a parabola. And I'd say, well, what do I make it go down to? So I'd have to know that value, and that value. So wherever there's a change, you need to cut
It's a local maximum or
Yes.
minimum.
Yes.
I have a couple questions about trust.
Yes?
If this is ED here, and this is 30, how do you get the 10? Or do you take the angle here and this one is 10?
No, this is 30.
Oh, you use this one.
Yeah. Yeah.
Project 3 report, can we use sections from project 1 as long as we say that we have used it for project 1? Like
The section.
section like introduction or the values and calculations.
You have to bring your loads to
Yeah.
project one.
So we have to write it that on the front page.
Yeah, in the front page it should say the loads brought in project one, concrete, 150 feet, weighs this much, live load for KPA.
So after introduction we should have which are the aspects of
You can't just have numbers appear out of nowhere. You don't have to recalculate. Okay, so they're in the office.
Are they in the office?
Yeah.
So just go over.
Just go away.
Okay, so
Just for a project 3, so you know when you decide the cost of the positional area of the top and bottom as well, so the same size.
I said average, don't worry about the average bit.
Yeah, so we have the same size for both. Is it alright if we do the cross-sectional area below the outer dimensions for 1 square centimetre?
Well, you can just take it out. If you've done that already, it's similar. Don't worry about it.
My marks were added up incorrectly.
Okay.
I was wondering if I could show you the run it later.
Can you? I'll look at it after and I'll correct it.
Yeah.
So okay.
Oh, it's just been added up incorrectly. So I've got 6, 10, 11, 8 and a half.
So 8 and a half, 18 and a half, 28 and a half, 34 and a half.
11. Oh, unless. Oh, maybe that was it.
Yeah. No, I think.
So that wasn't part of the.
Oh, hang on, how did you mark that? Maybe you're right. Should have put a mark at the top. 1, 5, 6, 7, 8, 9, 10, 11.
There's just a marker.
Yep, okay.
I just need that updated, right?
Oops. Oh, I'm making a dog's breakfast of this. No, don't go yet. Now, check when it gets uploaded that it is what it is, and if it's not, just say, Lizzie, you changed it and you forgot to tell me to do it. Okay. Okay, quick ones?
Can I take that?
Yes.
Thank you.
My test of writing up, like not my computer. My tutor did
Might be in there.
the check answers
Okay, then it will be in there. How do you think it's what do you mean? So you're going to write the stickers of all the dreams you've got? Yeah? And, sorry? The moment of inertia. No, from the tables. Yeah, you come up with a beam that weighs 14 UD, whatever, you look up the eye value and say that's the stiffness. Now for the full span, have you done the full span? And what member? Have you got?
I don't think I can make it.
Sorry? What member did you choose to span 36 metres? You can't remember? That's usually something that stands out in people's minds. Sorry?
You just get it off the table.
Yep, get it.
If I have a question about that, as in a marks question, do I come to you or my tutor tomorrow? Alright, we'll do it now then.
Can we do it after?
Yes, although I was going to go.
Well, I've got to get going.
Yep.
You can leave it with me and then I'll put it in the picture. And I'll put it
I've got my thing tomorrow. Can I just do it tomorrow? Or should I I'm keen to join, but they won't know. I don't know if they need it too. I wasn't sure. It's a really quick question. Because if I put 0, then I'll just leave it. For this calculator at the moment, in this location, where you put 0 and 4, where we should that count? I was ready for the thank you.
Who's that with?
Sim.
Okay.
Thank you.
Okay, quick ones, we've got to get going, maybe after.
I just want to ask you a question.
I don't want, can I go through the question and you can see where you lost marks?
It's just one mark.
Well, it's now 40 minutes.
If you integrate that, so you essentially just
Is that
with a step not.
What if he's got the right equation?
Yeah,
if you've got the right equation.
Yeah, but I'm saying, is that
If you've got
the
right-
only way of solving that? Finding the common equation, or just finding the equation of this?
Yeah, finding, no, I would find the equation of this.
Yeah.
That's how I
That's what it is.
Instead of integrating, can you just integrate and make that equal 0?
If you integrate this, you'll have problems with your boundary conditions.
Yes, yeah, that's.
So that's it. You may have problems.
Yeah, too easy. So just.
Yeah. Okay, can we ask me after?
Quick question. Task 5, do you require pictures of the structures we're talking about?
I don't require pictures, but I'm being picky this year and I require details.
Details.
Okay, with respect to task 5 on the project, can we talk after?
Okay.
Yeah. With respect to task 5 on the project, God, did all those people leave and not go, thank you, Lizzie, goodbye? Yes, they did. It's not good enough to go, Menzies building, put a shading on it. Okay? I need details. I need north side, put shading, make it vertical, make it horizontal, propose to put trees there, propose to put this there, propose to put that where. You're saying put solar panels on the roof? Okay, what's the area of the roof? You can Google quickly how many panels give you how many kilowatts, so you can say based on that rough approximate area of the roof, that would produce approximately so many kilowatts. Okay, so I need more details, none of this just general wishy-washy stuff. That's why last year they were asked to look at 10 locations, you're asked to look at 5 locations, so you need to provide a bit more. Put a water tank on, where do you propose to site the water tank? Any idea how easy it is to get to the existing plumbing? You know, you may not have an idea, but you may have to, you should say in there, this is the proposal, not quite sure how easy. You would then have to look into how easy it is to access existing plumbing in order to connect the water tank up to it. That sort of thing. Okay, moving on. So, the test paper. I'm going to primarily focus on question 3 because that is the question that was the worst done question. I believe the average, not 100% sure, but I think the average percentage was about 67% for this paper. You've got to mark out of 45, get your calculators out yourself. I'm not sure what that relates to. So, I've chosen, this is from paper A. So I'm not going to go through all 3 papers. There were 3 papers. In the top corner you'll see an ABC. So all the papers are different but similar. So therefore if I don't do your particular question, actually take that as an opportunity to actually write the question down yourself so you can actually give yourself another go at doing that question. I am not going to post these inkings. You want to see the answers, you can go and look at the video recordings, but I don't believe in posting solutions to papers you do. You should be, you can post answers, or you can Answers if required, but no solutions. I'm trying to wean you off solutions. You're too addicted to them. Okay, question 1, I will not do the entire question here, and I covered this effectively already when I did the equilibrium equation. Where people went wrong, when they put their unknowns in here, bx, by, ay, and they took moments at A. Everyone, I think, said, okay, it's 2 times 5, vertical load, horizontal distance, it's going clockwise. And then they looked at by and said plus 10 times by equals 0. And what you did was you forgot about the horizontal force. Once again, that horizontal force, if you trace that arrow, extend that arrow line either way, it does not run through point A. That means it causes a moment. What is that moment? I stick my finger. This is what I do. I stick my finger on point A, plonk, and I make my other finger follow the arrow round, and I go, ooh, forming a circle. That's anti-clockwise. So in here I would say plus 15, horizontal force, vertical distance of 1 metre, times 1. So, again, don't forget you have a horizontal force in there. It contributes to the moment. And I think that's enough about question 1. Question 2, I'm not even going to do at all because question 2 was well done. So well done, pat you on the back. I seem to put you down quite a bit, but well done. Question 3. Now this question 3, I believe, is paper B. So this is from paper B. But as I said, therefore go, that's great. I can use this as an opportunity to get another question, and then I can work through how I do it. Okay, each of the papers had a beam with overhang with an applied moment. So therefore they were different but similar. Some had UDL loads that weren't continuous. Some had a UDL load that wasn't continuous and point loads as well. So the first thing you need to do here is calculate your reaction. So I will do, because we do have time, this question entirely because it was poorly done. So I'm going to calculate my reactions first. Now there is a horizontal reaction in here. Because you're asked, if you are specifically asked to calculate reactions, you cannot forget about AX. You'll lose half a mark. If you're not asked specifically, you can say, oh, I know that horizontal force doesn't contribute to the bending moment diagram, so I'm not going to actually calculate it. I can draw it in. I'm not going to calculate it now, but we all know, looking at that AX equals 0. So taking moments at A now. You couldn't have waited? Oh, well, what oh, okay. I'm glad I've been helpful for another subject. You're welcome. Okay. Could have left earlier, though. Okay. I'm going to come up with my equivalent point load. And we all know that equivalent point load is equal to 12 times 467. When we position it, we have to position it in the middle. So in the middle of 4 plus 2 plus 7, in the middle of 7 metres. So that means 3.5 metres from one side. So as I'm taking moments from A, that actually will be positioned 2.5 metres away from A. So far so good? So taking moments at A, some of the moments at A equals 0. I can put my 50 on first. That 50 is causing clockwise rotation, so it's minus 50. So where a lot of people went wrong was they didn't get the reactions right. Bummer, but you won't make that mistake again. You have minus 50, then you have your total load, minus 12 times 7. And we look at the perpendicular distance from A, so times 2.5 metres. And then we have plus 4by equals 0. So by is equal to 65 kilonewton. And then just so I can be complete, forces in the y direction, AY plus BY minus, we know 12 times 7 equals 0. So AY works out to be 19 kilonewtons. Okay, so we come along here. BY we said was 65 and AY was 19. As soon as there's a moment in there, I don't like trying too hard with my deflected shape to start off with. So we know this load will make it come down somehow, but you know, we can imagine something like that, but we'll wait and see. So shear force diagram, always the easiest to start off with. Start at the left-hand end. Shear force starts at 0. If you didn't put units, you would have lost, I think, half a mark. Why, Lizzie? I got the numbers right. A number's a number. Without a unit in engineering, it's useless. Okay? Okay, we start at the left-hand end and we follow the load. And what is the load doing? It's reducing. It's negative. It's dropping by 12 kilonewton per metre every metre. So therefore, by the time I move across 1 metre, it has a value of 12. My reaction here is a total of 19, so I step up a value of 7. A bending moment does not affect the shear force diagram, so you don't worry about the bending moment. Now the load continues to drop by 12 kilonewtons per metre. So now, in actual fact, I said the slope of your shear force, dV dx, actually is equal to W, which in this case is 12 kilonewton per metre throughout. So when I draw these slopes in here, they should all be parallel to one another. So I'm going to try and draw this parallel. So that now continues to drop a further 12 times 4 metres, 48. So it gets us to a value of 41. Then we step up a value of 65. And again, trying to draw a parallel line in here. Sorry, we step up total 65 to 24, and then we end up at 0. So in this instance, our shear force is linear throughout because we have a UDL load on throughout. For cases where people didn't have a UDL load, your shear force can just continue horizontally across. There's your shear force diagram. How about everyone that got it wrong and everyone that didn't have paper B now? Pull out a piece of paper and attempt to draw the bending moment diagram. We have time. So remember, dm dx is equal to v. So how about I give you 5 minutes? Find where is your bending moment 0? Note those points. And then on your diagram, go positive shear force, downward slope, negative shear force, upward slope. Do it now. Why not? Is he in the room? How are we going with that bending moment diagram? Okay. So, where is my bending moment 0? Bye. At a cantilever tip. 1, 2. and it may be 0 somewhere else, but I don't know where. So now I say to myself, negative shear force, upward slope, positive shear force, and I mean the value. This is a negative value. I have a negative value of shear force. It means my slope. So this, as well as being V, it's also dm dx. So this is telling me, if I ignore the fact this is the shear force, I can say what this is saying is my bending moment slope is 0. The gradient of my bending moment is 0. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that works out to look like not a very well drawn parabola. Can you see here my slope? It's 0. And can you see the slope is getting bigger and bigger and bigger? Okay, now I have a positive shear force, so that's a downward slope. Then I have a negative shear force, so that's an upward slope. And then I have a positive shear force, so that's a downward slope. Now, there are two ways to calculate the value of that first bending moment, that bending moment up here. One way is to use the area method, okay? So I can work out that area in there, and that area in there is 12 times 1 metre divided by 2. Please remember the area of a triangle is half base times height, okay? People forget to halve it. And that area in there works out to be 6, so that moment up there is 6. Now, you also have the option where you can create a free body diagram, 1 metre long, and you want to know what this moment is at the cut, and your load is 12 kilonewtons per metre. So you can take moments at the cut, and you'll have m minus 12 times 0.5 equals 0. And I'm saying minus, and you should all be going, but isn't it a plus, Lizzie? Yes, it is. And from that, my bending moment is 6 kilonewton metres. Now, that's a longer way, I will admit. However, if you now say, oh, there's a moment applied. Oh, God, I forgot if it steps up or if it steps down. Oh, my God, does it step up or down? I don't know. And you panic. You turn the page, you go to another question. But when you come back to this question, okay, you would say, okay, I'm not going to use the area method. What I'm going to do is I'm going to cut my beam again. I've got 12 kilonewtons per metre. I'm cutting it at 1 metre, and this time I'm saying I have my 50 on there. And at the cut, so maybe I'm cutting at 1.0001 metre. So I include the 50. So now, if I take, what I'm just going to do is I think I can take that off without causing you too much grief. And I can just write over here, slope of shear equals W. So dB dx is equal to W, which is 12. So coming back up here, I'm now going to take moments at the cut. I have M, I have minus 50 because it's going clockwise, and then I have my plus 12 times 0.5 again. All of that equals 0, and from that, my bending moment now is equal to plus 44. So I actually love equilibrium. Equilibrium will tell you the sign, it will tell you everything. Because it's a plus, you know your bending moment value now suddenly steps down to 44, and that step in there, of course, is equal to 50. So, according to our upwards-downward slope, my bending moment continues to move down. And then you can see here, my shear force passes through 0. That means my slope, dm dx, equals 0. And what does that mean? It means I have a local maximum. Now, people are asking me, what do you mean by local maximum? It means just at that local point. It could be an overall maximum or just a local maximum. So on the paper you are asked, if you look at the question back here, to show all values, to show values of all local maximum or minimum values. What that means is you had to calculate the 6 and define the 44. Now, because my shear force diagram is linear, my bending moment I know is a parabola, and it steps down a bit, and then my slope changes, and I haven't drawn a very good maximum there. But my bending moment diagram then looks like so. Oh, can I just erase that out and try and draw that a bit neater? Okay, let's give this another go. So I have to have a maximum here. Now, how do I know how far up to bring it? So this value here at B, the value of the moment there, I could say that's equal to area 1 plus area 2 plus area 3, or I can just say it's equal to the negative of area 4. And to be honest, area 4 is far easier to calculate because it's just 24 by 2 on 2, which is 24. And that area is a positive area. So because I'm coming from the other direction, that means this moment here is a negative moment. Remember, I draw positive down. So I have a value of 24 there. So I have one thing left to calculate, and that is that maximum value there. We know it's greater than 44, but what value does it actually have? In order to calculate that value, again, you can use the area method. Now, in using the area method, you need to know what that distance is in there. I'll call it Z. So, looking at that triangle there, we know the slope of this line is 12 kilonewtons per metre, and we know the height here is 7. So we're using this relationship here. V is equal to dx is equal to W, and from that you get a Z value in there of 0.5833. So everyone clear with that? I want you to leave understanding how to do this. So therefore, that area 2 value, when you work it out, it's 0.5833 times 7, once again, on 2. So the value of the moment here now is area 1 minus the moment, take that. Now, in saying using the area method, don't use the area method. What am I saying? The area method now, you go, hang on a minute, I've got the 50 in there as well. So I'm totally confused by what that value is there. So once again, if you are totally confused by what it is there, what you should do is actually cut the beam at 1.5833 metres. That's 19. Shh. That's 50. And when you take moments at the cut and you equate them to 0, that will give you a maximum moment here equal to 46 kilonewton metres. So that maximum moment is 46. If you want, you could calculate that area, take it away from area 1 and take it away from 50, but you're going to come up to me after and say, do I take it away or do I add it? And what I would say is don't use that method if you're confused. I don't use that method when I'm confused. I cut the beam. Equilibrium works every time. Is everyone okay with that part of the question now? Okay. Go away and have a look at it again. I know sometimes you're like, oh, I'm not sure. I need time to myself. That's cool. This bit here gets put in because we know that people don't know how to do it. Sorry, we've got to lose marks. You've got to lose marks somewhere. From my bending moment diagram, I can now decide, or I can now look at my deflected shape. because we said we have a point of inflection when our bending moment passes through 0. So that means at that point there, we have a point of inflection in our deflected shape. Shh. And it also means we also here, because my bending moment passes through 0, have a point of inflection in our deflected shape. So now when I go and draw my deflected shape over here, I go, okay, I have a point of inflection here, so I know I've got tension on the top here, and then my point of inflection, I'm going to exaggerate it significantly, comes down, and then I said I have a point of inflection. Whether you drew that up or down didn't matter, as long as you indicated you had a point of inflection here. So thus, you know your first point of inflection is exactly at 1 metre. You need to find where that is. Because the question is asking you calculate the exact location of any points of inflection. So how do you do that? We know it occurs when our bending moment is 0. So what does that mean you have to do? It means free body diagram. You've got to cut the beam either looking at that free body diagram or that free body diagram and come up with an expression for your moment and then equate it to 0. Now this is my preferred side because it has preferred free body diagram because it has no moment applied to it. So how you would proceed now is you would then say, okay, I'm going to draw that as a free body diagram. I have my reaction force here, which is 65. That's 2 metres. My load here is 12 kilonewtons per metre. I'm just going to define that as x because that's easier, because I know where my bending moment occurs. It occurs somewhere in there. So I draw my moment, my unknown moment. This time I draw my unknown moment clockwise. Why? Because we always draw our unknowns positive, and remember a happy face is positive. Okay, so now I take moments at the cut and I equate it to 0. So I have minus m, and then I have minus. If you don't want to make that x, you can make the whole thing x. It doesn't really matter. Okay? So I have minus 12 x plus 2 all squared on 2 plus 65x. So I'm taking moments at the cut, so the 65x hopefully will be clear to you. Where did I get this 12x plus 2 all squared on 2? Well, my total load down here from my UDL load, that total load in there, well, it's 12, and my distance here is x plus 2. So that's what my resultant load is. Now, when I position that resultant load on, I position it in the middle of my distance, and therefore that's why I squared that and divided by 2, because that equivalent load is being positioned. I'll draw it on this side because the other side's a bit messy. X plus 2 on 2 away. So that distance on the other side is similarly x plus 2 on 2. So there is my expression for my moment. And when I simplify it all down, I get that expression for my moment. So that is an expression for the bending moment, not everywhere, but through from this point B through to the other point. Why did I just change? Why didn't I show you on here? This expression is valid between x is equal to 0 at B through for 4 metres, because I've got no singularity brackets in there. So now what I have to do is I equate that to 0. And when you equate that to 0 and you use your ax squared plus bx plus c equals 0, and you solve for that, you will get an x value in there of 0.6466 metres. Okay? I'm not going to do the algebra for you. Go away and do it yourself. Yeah? Is that okay? The last question again was done relatively well. Where people had issues, they didn't recognise the section was symmetrical about the xx axis. I'm not going to do it. You didn't need any shift values in there. All you needed to do was a BD cubed minus BD cubed, irrespective of your shape. And then to supply the my and I formula, knowing that the biggest moment here was at the support. Okay, give me 1 more minute. Shh. Good luck. Work hard. And whatever you decide to do, I hope you do really well at it. If you do civil, I'll see you all next year in solid mechanics. But otherwise, work hard. Did you learn something? Did you learn something you can just look at? Do you actually look at structures differently now? Forget about the maths. Do you kind of go, oh, that's a truss? If you do that, that's what I'm the most happiest about, that you actually look at a structure and go, how is that standing? Okay. Good luck with the exams.